Hi. So yeah, we're going to be talking about some of the research we've done into VPN clients. We'll go through some of the methodology we use. We've got more shells you can shake a stick at, and then we'll go over some of the defense and mitigations. So that's me. That's what happens when you pick a Twitter handle in 2009, not thinking you're going to use it. There we go.
Hi, I'm Rich Warren. I'm a red team operator from Amberwolf. My handle on Twitter is Buffalo Overflow. I do R&D, tool development, stuff like that at Amberwolf, and have released a few tools over the years that you might recognize.
So who's Amberwolf? A new company-ish. We're just about to have our first birthday. Kind of red team focused, regulatory engagements, but also lots of vuln research and exploit development. So we're going to start with a bit of nostalgia. And this is our kind of brain dump of initial access over the years. And along the bottom is as new kind of defensive technologies have come in, attackers have had to adapt their tradecraft. And we think that our research on VPN clients and kind of client attacks in general fit along this timeline. So we'd hopefully agree by the end. And it represents a different way to gain initial access into a network. So what's an SSL VPN? From our kind of point of retrospect, and hopefully you'll agree too by the end, it's essentially just like a web browser, except it's a really rubbish one because it's got no sandboxing or protections or anything. So yeah, it's kind of just like a web browser without a sandbox. And there's a bit of a public perception of SSL VPNs. It's been driven by advertising and influencers. And they're the kind of privacy VPNs. So they give the impression that you can only ever bolster your security by having a VPN. And that's kind of handy for us because when people think of it as a security product, they trust it more. So if we tell someone to connect to a VPN, they think they're connecting to something that's going to increase their security. We won't be talking about privacy-based VPNs today. We'll be talking about some of the ones in the remote access category. Maybe some people in this room use or work for some of the companies in the remote access category. So we'll kind of go over the high-level components of an SSL VPN. You've got the server, and we've seen lots of bugs in the kind of server side. That's on the internet and bridges the internet side and the corporate network typically. And then you've got the client GUI, the bit that runs in the system tray, and lets users put in their credentials and put in the VPN endpoint, do some configuration. And then you've got the service component on the OS, and that's running with typically elevated privileges because it's got to do things like set routes, things that the user mode process can't do. And what we can focus on with our research and what we found was that there's an inappropriate amount of trust between all those components. So the kind of client GUI and the service component really trust what the VPN server is saying, and they'll just act upon instructions that it gives them. Okay, so this is oversimplified, but the point we're trying to get across here is that there's these bad VPN server vulnerabilities, but then the patch comes out and people patch their 1 or 2 servers, and the problem goes away and they can relax. And in contrast, patching the client seems to be a lot more complex, certainly from what we've seen. We've seen like massive inconsistencies, not only across organizations, but within the same organization. So different versions clearly demonstrating that it's a lot harder problem than just keeping a server up to date. So we kind of want to abuse this, the trust that the server has. So if the VPN client's a web browser, we want to be the web server and we want to tell it what to do. So we kind of set out to re-implement a lot of the VPN servers so that we can control the message that's sent to the VPN client. And originally we thought it'd be cool if we can control DNS, but then we quickly realized that you can do a lot more than that. I guess the message is like, what's the worst thing that could happen if you connect to the wrong VPN server? This started at our previous company where we released a tool called Drop Connection, which exploited Cisco AnyConnect. And we thought, well, we could use this on a red team engagement, and we did, and it was really successful. We compromised the target, and we released the proof of concept, and that, but we thought it could be something bigger. What if we could make a universal server that if you connect to it with any VPN, we could pwn you. So we did it. How this started off was we figured out how the clients communicated with the server and put burp in the middle. And I guess we were a little bit surprised that there's no real concept of like certificate pinning in the client server communication. So the only way to establish like, is it a legitimate server was, does it present a valid TLS set? And underneath all of the communications were kind of similar, just a different kind of data structures. And obviously as an attacker, we can create our own valid TLS set and host it on a domain. So none of this really matters, but we just thought it was interesting to see which ones validated sets.
Thank you. Right, so a typical part of every sort of SSL VPN connection is going to be, the first step would be authentication. So what's going on here is the client is speaking to the server and it's looking for a response from the server that says that they recognize as valid. And typically that would be, hey, please send me some credentials. And what we're trying to highlight here is that the client has no way of knowing that the server is legitimate or it's a fake server. All it's looking for is a response which it recognizes as valid. And so typically that might be an XML response, just like this one, asking the client for some credentials. And if we reply with the right XML, then it's going to do this prompt here and ask the user for some credentials. And if the user provides the credentials, it's just typically an HTTP post request. And if the user gives their password, we can capture that. So that's nice and easy. So why do we think this is better than traditional browser-based phishing? Well, it's hard to think that anyone would fall for this specific phishing website, but in general, users these days are trained to spot typical browser-based phishing, whether that's dodgy CSS or looking out for the little green padlock that says it's secure. But this is just a login box, right? This is coming from the legitimate client. There's hardly anything here to spoof. It's real. But maybe that you've got a technically savvy user, and perhaps they'll put in an invalid password just to see what happens. But we don't actually care. We're not validating the password here. All we care about is creating that connection and then abusing what happens after that point. And like we've shown, capturing credentials is great, but as we promised in the title, we want RCE. So taking a look at a standard VPN client, like what can the server make the client do? And there's actually quite a lot of things that can be configured on the server side that we can perhaps make the client do. So this might be installing things such as modules, certificates, updates, or it might be configuring things. So like Dave said, DNS, gateways, proxies, those sorts of things, making it make certain network connections, and actually maybe even running things. So things like post-connection scripts, which we abuse in many of our attack chains here today. So as I mentioned before, post-login scripting is one of those things that we abused. And two of the VPNs that we're going to be talking about abuse this feature. So typically these post-login scripting features are used to allow the admins to perform some action after the user has logged into the VPN. So this might be like mapping a network drive, or it might be pushing down group policy updates, but it just allows the admin to get the client to perform some action, or in our case, a malicious action. And another feature that we could abuse is auto updates. So these are typically used to keep the client up to date with the latest version. But a lot of the times what we found is that the client version is actually downloaded directly from the server that it's connecting to rather than from the vendor's website. And these are typically then run with high integrity, like Dave said, under the service account. And sometimes these will have cryptographic signing and hashing checks. Sometimes they don't. And sometimes we're actually able to bypass these hashing checks and signing checks.
All right, we've got the concepts down, so let's do some case studies. We'll start with the Cisco one. We'll skip over this fairly quick because one, it's public, and two, it's probably the most simple one out of the lot. And as Rich said, it uses the post-connect scripts to execute code. It was fairly simple to implement. It's a lot of HTTP requests, and then the only prerequisite is that the client needs to think that it's established a successful connection. So at the end of all these requests, it sends an upgrade to a connect request, and we just implemented a little loopback socket so that it could fulfill that request. And then as soon as it thinks it's connected, it will run the onConnect script, and that can be BBS, BAT, lots of different ways. So yeah, you're owned as soon as you put credentials in. Something we didn't kind of talk about in the previous research when we mentioned this was that in some situations you can abuse it for privesc. So the scripts are downloaded to this folder here, and they're written as system. So you know, if you can write and change that, delete that script folder, you can make a junction, and you can get it to write your file that you've served from your fake VPN server to anywhere, so system32, for example. But Cisco weren't that bad, so that, you know, the ACLs are okay. But in a very consistent deployment mechanism, we've seen this incorrectly configured. We won't go into that today, but yeah, we can chat to you later maybe. So I'll have a quick demo, see what it looks like for an end user. So they put the VPN endpoint in, they put whatever credentials they want into there, doesn't really matter. And then we get our Mythic beacon. We've used Mythic as a CT for this just because it's like cross-platform, so it works on everything because we've got some macOS stuff as well. So exactly the same flow on OS X, code execution via downloaded script as a low privilege user. So there's our OS X shell.
Right. So the next client we're going to talk about is Ivanti Connect Secure. So this was previously called Pulse Secure. Many of you will probably recognize that name. There's been various bugs over the years in this, but we're focusing on the client side here. So this is a vulnerability in the sense that it's actually a feature of the client, and it allows us to execute code as a user level privileges on Windows. So we already saw this actually highlighted back in 2019 in the infiltrating corporate intranet like NSA talk at Black Hat. And it's actually a feature of the VPN. So again, you can provide a post-logon script that is executed by the client on logon. But this requires a full fat VPN appliance, and we want to be able to do it without running a full fat appliance because they're expensive and hard to configure. And actually, can we improve this exploit to make it more slicker? So another common feature of VPN clients that a lot of them have is a URI handler support. So this is typically used by VPN vendors to allow users to connect to the VPN with low user friction. So able to just click and connect and job done. But this also makes it easy for attackers, right? It makes it easy for you to deploy your malicious exploit that is also just as easy. And sometimes, in fact, it might even introduce their own vulnerabilities into these URL handlers. So if you've not looked at URL handlers before, these are typically stored within the Windows registry, and you can enumerate them using just a small amount of PowerShell or a tool such as URL protocol view. So you can see here, you can see the URL handler and the path that invokes. And these URI handlers, like I said before, they can actually result in code execution or introduce code execution vulnerabilities in themselves. And an example of that, if you've not been to our blog recently, is our Cato client research, where we found it was a command injection vulnerability in the Cato client vulnerability URL handler. And it's not just browsers either that you can invoke these URI handlers from. So if you might be familiar with the Felina exploit, which is in Microsoft Word, and that just shows that although you can trigger these through browsers, there are other ways to exploit these. And to address a personal gripe, a lot of these are just a typical browser warning. It's not really a warning, it's just a pop-up that comes up, and if that's a typical way to use the VPN, then it's not really a warning. So what does the Ivanti Connect Secure URI handler look like? Well, there's actually multiple handlers. So the first one is the Pulse Secure and the Pulse Secure 2 handlers. So these are registered by the PSAL, which is the Pulse Secure application launcher, and you actually end up with 2 pop-ups. So you get the first browser-based pop-up, and then you get the second one asking you whether to click always or yes, and in both cases it will launch our exploit. And in the second case, so this is the more modern version of it that's created by the Jam UI client, and this is a typical fit client that you will see installed on an endpoint in an enterprise. And so this is the one we're going to abuse, right? So the Pulse Secure client, it just has a URI, and then in there you've got a URI for your malicious VPN server and a couple of other settings that you can set, such as username and whether to store it. And that's just going to create, first of all, the browser pop-up, and then you're going to get this second pop-up where the user can put in their username and password. Now, ICS uses a binary protocol, so it's slightly different from some of the other clients that we've looked at, which use just HTTP. But in this case, first of all, it's going to make an HTTP request. The server is going to tell it to switch protocols to this binary protocol, which is going to use IFT over TLS. And we actually looked at OpenConnect, which is a really useful project that's implemented a lot of the client-based protocol. So it really helps us with reverse engineering some of this stuff. So this is what the binary protocol looks like, right? So first of all, you've got your TLS layer. So it's connected with over a TLS socket. It's made the HTTP request. It's switched protocol. And then it's going to send these IFT messages over that TLS channel. These IFT messages, they wrap the inner layers. So next you've got your EAP layer. So this is going to handle authentication wrapped in the IFT messages. And then finally, you've got your AVP structures. So this is your attribute value pairs wrapped in the IFT, sent over the TLS socket. So on the AVP layer, this is where we'd send our configuration data, such as ipconfig, or in our case, sending the logon scripts to execute code on the endpoint. And this is what that looks like. So you can see here, we've got the HTTP request being made, switching over to the IFT over TLS, sending ePauth, and then sending back the AVP pairs to execute our code. And we've got a demo now. So this is just showing on Windows. So the user goes into their browser, they go to the website, they get that single prompt. They enter a password. It doesn't matter what they enter here. We accept it anyway. And then executes the OnConnect script. Right, so next we're going to talk about SonicWall NetExtender. So this is a bug which we reported, I think, in April 2024. It was patched by SonicWall in July as CV 2024-29014. And this is RCE on Windows' system, and it can be triggered by a URI handler. So it kind of ticks all the boxes for what we want as an attacker, and got a diagram of it here. So, but this story is actually quite interesting. So back in 2008, there was a talk at Black Hat, which is about abusing SSL VPNs. And there was a bug which was very similar to one of the bugs we're about to talk about. The only difference being that it was in a fairly older technology. So this was in ActiveX control used by SonicWall, but we thought it was similar enough to include in our presentation here. And it downloads a binary very similar to the one which we'll just talk about. So in January 2021, we found this similar bug. So as I said, it's the same bug, just in a slightly different, newer implementation of the product. And then with a one-line change to that exploit, we found another one in 2024. So it was a bug so nice, they patched it thrice. And just to show you what this looks like, so the client makes an HTTP request to the server. The server responds with this NX Windows vir, and they say, hey, we really need you to support this higher version of the client, so we need you to upgrade. The client then says, okay, and it downloads the NX setupu.exe from our server. Now we're going to talk about the 2024 bug. So fast forward to 2024, the previous bug's been patched. And what we found is that we could actually just, with one line change to our exploit, instead of serving the higher version of the NX Windows version, we could send the EPC version with OXFF, the highest value, and then that would cause it to download a different binary from our server. So in this case, it downloaded a binary called macagent.exe, which is the EPC client, which they use for network access control, and execute it as system. But it's actually quite different in this case. So instead of just downloading the executable and running it, there is actually a signature check. So we reverse engineered this, look inside anycore.dll, and there's a check here. So it calls WinVerify_Trust to make sure that it's been signed, but it just checks that it's been signed by a valid CA. So if you're able to get hold of a code signing certificate, you're able to bypass this check quite easily. So another feature I mentioned at the beginning of the SonicWall section is that it had a URI handler. So again, we can use this tool here. And what we found is that there's a URI handler which is installed as part of the SMA Connect agent, which is typically installed alongside the NetExtender client. So we reported the NAC agent issue to SonicWall, and they provide us with a patch for testing. And we thought this was interesting, so we wanted to share it here. So they added a subject name check, so alongside the WinVerify_Trust check to make sure that it was signed. They also added an additional check, which retrieves the certificate from the binary, and then it compares it with this string here, so it compares it with SonicWall Inc. So we thought, you know, this looks quite like a good check, but like, can we bypass this? And what we found is that PE binaries can have multiple signatures, and what they've done here is you've got your WinVerify_Trust call, which verifies that it's signed, and you've got the certifying certificate install, which is pulling out that subject name. Well, actually, WinVerify_Trust will pass if there's multiple signatures, as long as one of the signatures is valid. So what this means is you can sign it with an invalid certificate as the first certificate to pass that second check, and then sign it with an additional certificate, which passes the WinVerify_Trust. That's essentially a parser differential vulnerability. So we thought this was pretty interesting, and we Googled around, and what we found was that this actually seems to be documented by Microsoft as almost a recommended way to pull out the subject name from a signed binary. And actually, from looking around at open source projects, we've actually found further vulnerabilities where this code has been reused. So we think this is potentially an interesting area to look for bugs. And we've got a demo again, what this looks like. So executing via our URI handler. So here you can see the users click the URI handler. In this case, there's no prompt for a password. It just starts performing that upgrade, and we get our shell system.
All right, so we'll move on to Palo Alto GlobalProtect, which seems to be quite a popular VPN product. This one's awesome because it's Windows and macOS, and you get system and root respectively, so pretty good. We reported it in April. It hasn't been patched yet, so it is currently 0-day. Yeah, which is exciting, isn't it? So you might have seen, if you read it quickly on the previous slide, that Pan GPS, the service, installs any certificate that the server gives it. So this is that implied trust that we talked about. And it does this as system, and it installs it as a trusted root cert. And so can we, which is pretty good. I'll give you a couple of seconds to be shocked about that, because it's pretty bad. So essentially, like 2 HTTP requests in, we've installed a root CA on the target just by them typing in the wrong VPN endpoint. So what's the reason that they've done this? There is a kind of semi-legitimate reason. So you can see in that top flow there, that's what happens when the user initially connects to the VPN. They go to the portal, and that's got a DNS address, and that's where they supply their username and password. And you can obviously obtain a legitimacy certificate for that because it's a DNS address. And then it gives you back the gateway info, which is typically an IP address, which is obviously a lot harder to get a signed cert for, a legitimate one. So the solution is just push down your own CA, and then everything's trusted, so it's fine. So we'll take it from this point that we've captured the user's credential. That's kind of old news now. So we'll look into the step after that and what the server returns after the user's kind of tried to authenticate. So we've got a load of XML, and we found if we bump this version number, it's a similar story to some of the others, that actually we can make the client think that we need to upgrade, and we can provide our certificate there, and we can say, yeah, actually we do want you to install that into the trusted cert. So that's all good news, and we control all of that. What else do we control? So in that same XML blob, there's information about how the client should try and upgrade. So, I mean, transparent sounds good. We don't want the user to see. And yeah, we want to serve them the exploit and just get our shell back. But there are some prerequisites. Like the Cisco one, we need to make sure that the VPN connection completes. And we also need the MSI to be signed by Palo Alto. So to kind of get it to complete, we needed to know what the VPN connection and underlying protocol looked like. So what we did is we just disabled all the cipher suites that Wireshark was unable to intercept and decrypt, and then we just started the session and captured that, and we quickly just pulled out this transfer from HTTP to like a binary protocol, and you can see the start tunnel and then the start speaking binary there. And this is the structure of that binary data. So you've got these magic bytes, and they're in both the request and the response. It's kind of a standard like length and data structure, and the data is actually just like an IP packet. So we can kind of mock up forwarding that on and do like a whole re-implementation of the VPN if we want to. But all we really need to do is respond in the right way at this point to get the VPN client to think it's connected. And at that point, all we need is a signed MSI. So this is us kind of intercepting the traffic just to prove we could. So it's like pulling out those data structures and with Scapy and like parsing them, and you can see that like we can see all the data that's going over the VPN at that point. So at this point we need a signed MSI. Not a problem, because we've got our CA on the box, so we can sign it with whatever we want. The important thing for us is that once we've got the shell on the user's box, we also want them to still be able to connect to the corporate network. So we took the approach of backdooring a legitimate Palo Alto GlobalProtect MSI and then re-signing that. So we're kind of being nice to them. We can even upgrade them, or we can downgrade them. So it gives you the option, there's an older version available. Would you like to install it? And that's quite useful, because even if this gets patched, in theory, we can just install an older version again and then just re-exploit them. So how do we do the re-signing? It's just the commands we use here. MSI patch has got a lot more in it than, there's a lot of work went into that. But essentially, yeah, just remakes the MSI and then we can re-sign it on the bottom line. And what we end up with is an MSI that gets run by MSI exec after the connection's established, along with a load of CMD invocation that we haven't really looked at. So we're really happy. We thought, I would better check this on a few other versions. And it didn't work, and we were really sad until we realized that actually the particular version that we picked to test it with next, the update mechanism was completely broken on that whole version. So if you've got that version installed, you're never upgrading. So we can't own you, but you're also stuck on that version. So we had a look at OSX, and other than it being a PKG rather than MSI, the flow just kind of worked, and it got up to the point where it did a signature check and then obviously failed. So we had a look at how it was doing that, and it turns out it's just PKG util, pipe to grep, and quite a greedy match on that developer ID. If you saw You're Muted Routed talk by Patrick Wardle at DEF CON, Black Hat, a few years ago, then this might look familiar. So we were able to satisfy that, obviously, because we've got a CA on the box again. And this is our signed package file. It's marked as signed and trusted by suspicious package, and what's your sign? So all good, all trusted there. A little demo. So this is what it looks like. Again, it doesn't matter what credentials the user puts in. And they kind of connect. And then you'll briefly see we're updating a product. So now it's running our MSI and we get our system shell. All good. So now the same thing on Mac. Exactly the same flow. Credentials in, pulls down the package. Package is signed, checks it, installs it as root. And we've got our root shell.
Thank you. So if you've been paying attention, when you've been watching the demos today, what you'll have noticed is that they're all connecting to the same server, the same DNS name, so it's a connect.natrovpn.lol. NatrovPN is our project that we created to emulate all of these VPN servers and execute code. So that's the tool that we're going to be releasing soon. So the way we've implemented that is it's essentially a reverse proxy setup that's Dockerized, and we have the various VPN containers that emulate each of the VPN products that we've talked about. And then we perform some fingerprinting on the front end on the reverse proxy to identify each VPN product that's connecting to our server. And the fingerprinting might be under the guise of things like TLS handshakes or SNI, or in some cases the lack of SNI in the case of like Palo Alto, where it's connecting via an IP address. Or we can look for things like the user agent or the URI string that it's connecting to, as well as like things like URI handler enumeration with JavaScript. And we're going to release the NatrovPN tool, and we're actually going to do a blog series around some of the deeper dives around some of these products, because I appreciate a lot of what we've gone over today has been fairly high level, and there's a lot more involved in this. So please look out for our blog posts in the coming weeks. One more thing is that this actually works on mobile as well. So we've just got a short demo here showing, I think this is the GlobalProtect iOS client. So we thought this was pretty interesting. You can download an official client from the iOS App Store, talk a user through connecting using this official app. And at that point, we've obviously got a man in the middle position on the user. And we're kind of interested in taking this research further and seeing what we can do after that point, you know, things like injecting perhaps an MDM profile or something like that. So we've got some FAQs around what we think are common questions around this. So why would anyone actually connect to the wrong VPN in the first place? Seems like a pretty stupid thing to do. Well, as we said before, this has been really successful for us in phishing, red teaming phishing attacks, where we found it actually is more successful than email-based phishing. So we've had lots of success with this. And then why not actually just run a bunch of like actual VPN servers that are configured maliciously? Well, and obviously there's the cost involved in that. So like buying 4 appliances and licensing them is extremely expensive. The ability to accept any credentials. So as you've seen, like the user logs in with any credentials, we don't care what they are. We'll take a copy of them, but like most VPN products are going to need to validate those credentials. And then we also want to be able to serve things that aren't actually legitimate updates. We need to sign them with our own key, backdoor things, etc. And then there's some like abnormal client server flow where we're doing things that aren't necessarily supported, but we're abusing some of the use cases here, and exploiting vulnerabilities that might be in legacy code that aren't necessarily being exercised by a real server that we can do with a custom implementation. So we'll go over some defense here. So how can we protect against these attacks? Well, we've kind of split these into sort of the generic mitigations and then some like vendor specific mitigations. So from a generic point of view, we can really try and stop users from connecting to illegitimate endpoints. So we can do that through things like host-based firewalling. So whitelisting the VPN endpoint so that the VPN client can only connect to the legitimate endpoint, and that kind of like stops the attacks in general. From a vendor-specific point of view, a lot of these clients and products will have a feature to stop the user connecting to arbitrary endpoints. But what we found from doing red team assessments is that you can, in some cases, talk the user through undoing that mitigation because it doesn't require elevated privileges to do it. Or if you're coming from a malicious user perspective where they're doing it to elevate their own privileges on an endpoint, then that's not going to be enough. And then you can do things like WDAC and app blocker to application whitelisting type stuff to try and stop unknown scripts or executables being run. and obviously setting the correct file permissions to make sure users can't escalate privileges. And then from a sort of a detection standpoint, you can look for things like the child processes that are being executed by the VPN servers. Are they typical? Are they abnormal? And I think we've got an example here showing with Elastic. It's got a malware detection alert for the NAC agent being spawned by the NE service from NetExtender. Obviously, if it's typical for this to happen, then that might not necessarily be alertable on. And then you can look at things like application-specific logs for each of the VPN clients. So we've got an example here with the pangps.log, which shows that the user selected a new portal. And then depending on what auditing you have in Windows, so I don't think it's default, so you'd have to go and enable things, but things like auditing on files in the registry, because a lot of these settings are set in the registry, and new certificates being installed in the root CA store. And that's all we've got today. So we're happy to take questions if anyone has any.